This is the second of 3 parts for lecture 26 in differential equations and linear algebra. Of these 3 parts, this is probably the longest and hardest one, but I also think it's perhaps the most interesting. We're ultimately looking at bifurcations of a 1-parameter family of 2-dimensional systems, looking at the trace-determinant plane as I introduced in lecture 25 to help us understand what's going to go on here. As in lecture A and as in lecture C, we're going to use Mathematica quite a bit to help us both do calculations and make these pictures. So hang on and get ready to put a lot of ideas together in this lecture. This first slide that I want to show you for this lecture is what I showed you before in the last lecture. I don't want to dwell on this slide here very much because I showed it to you before, but let me show you what's on the slide for your reference as I make a drawing. As I make a drawing of the trace-determinant plane. Very important tool to help you understand what's going on with bifurcations of 2-dimensional linear systems of differential equations. What is the trace-determinant plane? It is a plane. Plane of this board here. You've got axes. You label the axes T, D for trace and determinant. Realize before I make any drawings that what I'm about to draw is not a phase plane. It's not solutions of differential equations. It's a parameter plane, you might call it. It helps us understand when bifurcations are going to occur. That's its main use. To help us make sense of all this, actually, and there's one thing missing here, the last condition that it's a saddle point when D is negative. In fact, let's go ahead and start there. If you've got a 2-dimensional linear system like this, where D, the determinant, is negative, the origin will be a saddle point. So down here, underneath the t-axis, you're going to get saddle points at the origin for such linear systems, whenever the determinant is negative. Hey, that's a pretty quick characterization of what happens when D is negative. Will they be the same saddle point no matter what D is? Same kind? No, it'll be a different system. It'll be different solutions, but the origin still will be a saddle point in those cases. The t-axis where D is 0 is evidently important. It separates saddle points from all other kinds of behavior. It's called a critical locus. Critical locus. The word locus essentially means curve of points. It is critical. It's important. It separates saddle points from other kinds of behavior. But there are 2 other critical loci. Loci is the plural of locus. One of which is the positive d-axis, where t is 0 and d is positive. As we've seen before, actually, that separates sinks over here from sources over here, not distinguishing between spiraling and non-spiraling. When t is 0 and when d is positive. We looked at that in the context of a bifurcation for a harmonic oscillator before. The sink case is when t is negative, which you see right here, and also right here. The source case is when t is positive, which includes this case and includes that case as well. That's another critical locus. Again, it's the positive d-axis where t is 0 and d is positive. The final critical locus, not sure if we can see that word locus or not, L-O-C-U-S is what I wrote there, is a parabola. That's also a critical locus. The equation of that parabola is d equals t squared over 4. It's called the repeated root parabola. When d equals t squared over 4, that's when the thing under the square root in this formula for the eigenvalues is 0, and so you get just one real eigenvalue with multiplicity 2. It's a repeated root. That separates spiraling from non-spiraling. Over here you've got spiral sinks. Excuse me, non-spiral sinks. I'll just abbreviate it, real sink. Real sink. In here you've got spiral sinks. Over here you've got a spiral source. And over here you've got a real source. But this description does leave out what happens on the critical loci. We actually did see what happens along the positive v-axis. There you get what's called a center. We saw that for the harmonic oscillator. In this lecture, I'm going to show you what happens along the t-axis, where d is 0, and along the repeated root parabola. We did look at a little bit of that before, but I'll go into more detail in this lecture. So the main purpose of this slide is just to help you understand that picture. If you want to pause it, download the PowerPoint, whatever, it helps you understand it. And make sure you can check everything, that it really works. All right, now let's get into our main application of all this. A one-parameter family of two-dimensional linear systems. It's a family. It represents infinitely many differential equations all at once, with a parameter I'm going to call, like I did in chapter 1, mu. Here's our family. dy dt is a sub mu times y, where a sub mu is this particular matrix that you see here. A sub mu is this particular 2 by 2 matrix. Depends on mu. How you think about this is key. For any fixed value of mu, this gives you one system. For any other fixed value of mu, it gives you another system. It gives us an infinite family of systems. We're interested in knowing how the behavior of the phase plane changes as mu changes. And are there any bifurcations? Like in the number of equilibrium points or their type from sink to source or saddle to sink or whatever? Can we find those? That's what we're after. And the trace-determinant plane helps us. It's a tool to help us. What kind of bifurcations does this system undergo? And we are looking at analytic bifurcations, what I call analytic. We're not distinguishing between excuse me, we are distinguishing between spiraling and non-spiraling, whereas a topological bifurcation you would not. Let's start by watching what happens on Mathematica. Just make observations of what we see. So I can enter all this stuff here. This pic code just makes pictures for different values of mu. I want to animate this. So here we go. This is what I want to observe, is this code, the output of this code right here. As mu changes. Make it a bit smaller here. Okay. Oh, it stops when you don't see mu in the picture. That's unfortunate. I need to make it smaller still. Let's start at the beginning again. What do we see now? We see a saddle point. Stable in this direction, attracting in this direction, unstable or repelling in that direction. You see a magenta and a brown line. Those are null lines. X null line is brown, Y null line is blue. Notice how solutions cross it. When those null lines merge, all of a sudden something weird happened there. A bifurcation must have happened because now it looks like the origin is a sink instead of a saddle. Started off perhaps non-spiral, but it's definitely spiraling now. At some value mu, do we transition from sink to source? Or maybe to something else? We actually transition from sink to saddle point right now. It actually did not transition from sink to source. It's now back to being a saddle point. Source in this direction, sink in that direction. Mu continues to change. Evidently, when the brown and pink lines merge, we're going to get some other kind of bifurcation. And weird behavior right now. And now we're back to a case where we have a source, it looks like. Is it spiraling? Well, kind of, and well, now it definitely seems to be spiraling at this point. We're almost to the end. Value mu. I'm letting mu go from -2 to 2 here, by the way. Let's run it a little faster this time. Increase this animation rate. I'm going to run it 4 times faster now. Saddle to sink. Right now, non-spiral to spiral. Spiral sink to saddle point. Saddle point back to source. And then a spiral source. So our goal now is to understand what's going on here. Can we understand it? Can we find the bifurcation values? We need to, again, think about the trace-determinant plane and do some algebra. The trace of this matrix, remember the trace is the sum of the numbers on the main diagonal. Mu plus 0 is mu. This notation is emphasizing that I'm going to think of this as a function of mu when I make a graph in the trace-determinant plane of the values of t and d, where it's really going to be a parametric curve. It's not solving a differential equation, but it is a parametric curve. This is abusing notation, t equals t of mu. Don't worry about it. I didn't have to put the t of mu in there, but I decided to. The determinant, mu times 0 is 0 minus this times this, gives you positive mu times this, which is, if you multiply it out, positive mu cubed minus mu. That's the determinant, which can be factored as mu times mu minus 1 times mu minus 2, which is what I'm about to show you here. For what values of mu does this cross the critical loci? Loci being the plural of locus in the trace-determinant plane, the TD plane. First, focus on where it crosses the t-axis, where d is 0. Yeah, I can factor the d function of mu like this, and I see that that's going to be 0 at 3 places. Mu equals 0 and plus or minus 1, or in order it would be mu is negative 1, then 0, then 1. That's where I get a crossing of this critical locus. Evidently, that's where I get a bifurcation from a saddle point to what do we see? We saw a sink. A real sink at first, then a spiral sink, though we aren't to the spiral sink yet, as mu just passes negative 1. Next critical locus that I look at is the positive d-axis, where t is 0 and d is positive. Where is t 0? Well, t equals mu, so it's 0 when mu is 0. Hey, a bifurcation already occurred there. So is this like a double bifurcation? Kind of. Evidently, we're going to cross the positive d-axis at the origin, which is, you might not say, not the positive d-axis anymore. It's the d-axis where d is greater than or equal to 0. Let's put it that way. Sometimes you can cross it where d is strictly positive. So you need to think about where t is 0 and where d is positive. But in this case, t is only 0 when mu is 0, and d is not strictly positive there, it equals 0. What about the repeated parabola? That's the most complicated part. The equation of this parabola is d equals t squared over 4. So go ahead and plug in d of mu and t of mu in place of d and t in that equation, and try to solve for mu. D of mu is that cubic there, so that's mu cubed minus mu. T of mu is mu, so square that, I get mu squared over 4. Multiply both sides of this by 4, rearrange, factor out of mu. You'll get this equation. Another bifurcation evidently occurs at mu equals 0, so you can call it maybe a triple bifurcation. Yeah, because when you go through the origin, you're essentially passing through all 3 critical loci. But we're also going to get bifurcations where this quadratic is 0, which we need the quadratic formula for. These are irrational roots. 1 plus or minus square root of 65 over 8. You can double check with the quadratic formula. So the 0 matches the 0 here. This matches this. And these two numbers, if you approximate them, give you these two numbers, about negative 0.88 and about positive 1.13. I told you a few minutes ago, you could graph the points as mu changes in the TD plane. You get a parametric curve. In fact, since t is so simple, it equals mu, and d is this, d is really t cubed minus t, because t equals mu for this example. It's going to be a cubic curve. D equals t cubed minus t in this TD plane. Looks like this, that red curve that you see there. That is the parametric curve along which that point moves as mu changes. That's not a solution curve of the differential equation, even though I'm drawing arrows on it. No differential equation in this picture. Not a solution curve. It's this parametric curve as mu changes. It's useful to put the arrows to show where you're at as mu increases. And yes, we cross the t-axis when mu is negative 1. That's this point there. We cross from being a saddle point to a real sink. When mu is about negative 0.88, this one here, which is 1 minus square root of 65 over 8 exactly, you cross the repeated root parabola and you're into the spiral sink territory. Then when mu is 0, you cross to the origin, you cross from the spiral sink to a saddle point. When mu is 1, we cross from the saddle point to a real source, briefly until mu is 1.13, when we cross the repeated root parabola again, and we go from real source to spiral source. Very nice, don't you agree? I think that's really nice. All right, now we need to get into some deeper analysis of what's going on. What happens to the system at the bifurcation values? This first case that we're going to look at, when we cross the t-axis where d is 0, we have not looked at before. We have not thought about what happens when the determinant of the coefficient matrix is 0. We're now thinking about that here in those three cases where we cross the d-axis. At the t-axis crossings where d equals 0, the first case where mu is -1, what does the system become? What was the A matrix? A sub mu. I believe it was mu squared minus 1, negative mu, and 0. Yes, this looks consistent with that. That is my A sub mu matrix. And in the case where mu is -1, that matrix simplifies to what you see here. A sub -1, mu is -1, plug it in. You get this matrix. In terms of the vector field for the system, the vector field is -xx. If x is 0, that's the 0 vector, no matter what x is. Excuse me, I should say, if x is 0, that's the 0 vector no matter what y is. The infinitely many points along the y-axis, where y can be anything and x is 0, are all equilibrium points because they make the output of the vector field the 0 vector. If you're going to draw the phase plane, you put a bunch of dots, infinitely many dots along the y-axis. And those are parallel to the eigenvectors for the eigenvalue 0. An eigenvector for the eigenvalue 0 points straight up or straight down. For example, 0, 1. J hat is an eigenvector for the eigenvalue 0. Multiply this matrix times 0 for the first component and anything for the second component, you get the 0 vector. The eigenvalue -1, you can check, I'm not verifying it, has eigenvectors that are parallel to the line through the origin with slope -1. A general solution can still be found in this case with the same method as before. Take an arbitrary constant times e to the lambda 1 times t times an eigenvector for that, lambda 1. Lambda 1 is -1. This vector is an eigenvector for the eigenvalue -1. Notice this is actually a lower triangular matrix, actually. Its eigenvalues are on the main diagonal. -1 is an eigenvalue. Plus k2, another arbitrary constant, times e to the lambda 2 times t. Lambda 2 is 0. We get e to the 0 times t, which is 1, no matter what t is. That's going to go away. And there's your general eigenvector 0, 1, or any non-zero multiple of that. Simplify, you can write it like this or like that. If you solve a generic IVP, you can check you'll get this. You could solve it without the matrix exponential. You could essentially just jump right to here by setting t equal to 0 up here, setting this equal to x0 and y0, and solving for k1 and k2. In fact, k1 has to be x0. And k2, it looks like, must be got to be a bit careful here. If this is 0, x0, y0, when t is 0, k1 would have to be, e to the 0 is 1, k1 would have to equal x0, which is why you see x0 right there. And then negative k1 plus k2 would be y0. k2 is going to be y0 plus k1, y0 plus x0. You put that there. y0 plus x0. The x0 comes from the 1 minus x0 there, and the y0 is by itself there. Okay, you can check it on your own too. All right, next case, next bifurcation value. I am going to show you the phase plane for this, by the way. You may want to try to draw it before I get there. It's different. Infinitely many equilibrium points all on the y-axis. When mu is 0, it becomes this. Once again, we get infinitely many equilibrium points. They're all along the x-axis, where y is 0. If y is 0, you get the 0 vector, no matter what x is. So along the x-axis, where y is 0 and x is anything, those are all equilibrium points. You'd have infinitely many dots to draw along the x-axis. And in fact, that's the only set of solutions that are on straight lines. on a straight line in this example. The eigenvalue is 0, which is the only eigenvalue. This is upper triangular. And the eigenvalues are on the main diagonal. They're both 0. It's a repeated eigenvalue. Hey, yeah, we were crossing the repeated parabola, so to speak, there as well. But it only has a one-dimensional eigenspace, the x-axis. Check that. Here it turns out to be the formula for the solution. Interesting, this formula doesn't involve any exponential functions at all. It's linear in the x-coordinate and constant in the y-coordinate. All solutions, no matter where you start, must be horizontal, equilibrium points in the x-axis, and horizontal with evidently a leftward pointing arrow when y0 is positive, because of the negative sign there, and a rightward pointing arrow when y0 is negative. Go ahead and think about that some more. You might also want to just double check the matrix exponential. E to the t times this matrix equals this. The infinite series definition of the matrix exponential actually truncates because high powers of this matrix become the zero matrix. Go ahead and try it. At the other bifurcation value, mu is 1. This is the system. Once again, you get infinitely many equilibrium points along the y-axis. This is similar to case 1, except the other eigenvalue is positive 1 now instead of negative 1. That's the main difference between this mu equals 1 and the mu equals negative 1 case. Yeah, what do the phase planes look like? Here are the pictures. This is mu equals negative 1. That's the first case. The y-axis consists of infinitely many equilibrium points. I had Mathematica draw finally many there, but you should realize in your mind every point on the y-axis is an equilibrium point. All the other solutions head toward the y-axis as t increases. There is one straight line solution that heads straight toward the origin. It's right about here. And that does correspond to that other eigenvector, 1, negative 1, that went with the eigenvalue negative 1. So this is strange behavior. That is where those null lines crossed each other, where they merged, I should say. The mu equals 0 case looks like this, and yes, solutions are all equilibrium points in the x-axis, always going to the left and then above the x-axis where y0 is positive, always going to the right when y0 is negative. Strange kind of behavior. Strange things can happen when 0 is an eigenvalue. You get infinitely many equilibrium points, for one thing. And that picture is wrong. That's a typo picture that I didn't catch. The x-axis is not all equilibrium points. It's the y-axis that is, sorry. I will change this before I put it in the Google Drive. The y-axis is equilibrium points for this third case when mu is 1. The x-axis has blue arrows going through it, solutions cross it. Okay? It's a mistake. All right, so we can figure out what happens though, and we can write the general solution. What about the other repeated parabola crossings? At mu equals 1 minus square root of 65 over 8, which is about negative 0.88. I'm going to show you a bunch of approximations here. I'm going to show you the phase plane. Of course, you can always have your technology draw these things for you. You should realize that because I'm approximating this bifurcation value, that the approximate equations that I write down actually are not repeated parabolas. They're only approximate. Here's what I mean. If I plugged in this 1 minus square root of 65 over 8 for mu, it gets too messy. So I approximated, but as an approximation, it's actually not exactly right, and therefore it's not exactly where I'm crossing the repeated parabola in that cubic curve that went through the plane like this. I'm approximately there when mu is negative 0.8828. I'm not exactly there. If I were exactly there, then I'd have an exact repeated eigenvalue. Lambda's, it turns out, 1 minus square root of 65 over 16, where mu is this, same kind of thing over 8. Mu is the bifurcation value, that's the eigenvalue. And it's a repeated eigenvalue. It doesn't have a two-dimensional eigenspace, it's a one-dimensional eigenspace. It turns out it's the line y equals negative 2x. I did have Mathematica check all this. Turns out this thing is the hardest thing to figure out in this case. I had Mathematica do it for me. I did not want to do it. Some extra complications come up in the formula when you have a repeated eigenvalue in the form of getting extra factors of t, like here, 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 and here. I did allude to this in a simpler kind of situation with a harmonic oscillator scalar equation. We're relying on Mathematica to get that. I might talk a little bit more about that in lecture 27, but for the moment, we're just relying on the computer. And here's the phase plane. Doesn't look for sure whether it's spiraling or not, and in fact, at that exact value mu, it's not spiraling. You do have one straight line solution, y equals negative 2x. The solutions that are along this line are straight line solutions that head toward the origin, but there are no other lines that consist of straight line solutions. The brown and pink are still null lines. Every solution, and when you start over here, ends up approaching the origin asymptotically to this line. Solutions with initial conditions over here approach asymptotically to this line. That doesn't seem obvious, especially when you look at solutions that are like right here. It doesn't look like it's going to go kind of around the origin, but it actually does if I drew the line correctly, which I probably didn't. Should have drawn the straight line solution correctly. Same kind of thing over here. It's hard to tell, but these solutions actually would go past the origin before coming in tangent to this side. It's at the boundary between spiraling and non-spiraling. That's what's happening here. Once mu gets into the spiraling region, the null lines don't go away, but the straight line solution goes away when you are in the spiraling region. For the other bifurcation value, mu is 1 plus square root of 65 over 8, which is about 1.13, I think. I didn't bother finding the formula, but here's the phase plane. Interesting that these phase planes are kind of like opposites of each other. I didn't double check to see if they really are. The vector fields are complete opposites of each other. It looks like they might be. You might want to double check that to see. Switch between mu negative 0.8828 and positive 1.1328. Okay? Let's look at Mathematica, and then that will be the end of lecture B. Okay, and you can certainly play with this code if you got Mathematica and download it off the Google Drive. Here I can enter the matrix. Here are the right-hand side functions that I can animate. These help me animate the null planes. Pick a mu, creates a graph if I plug in a value of mu. For example, I can, now that I've entered that, I can plug in pick of negative 2, for example, get a saddle point. I can then put that in the animate function like I showed you before to animate it. And we'll do it once again. See those changes happen again. I'll let it run one more time starting from the beginning. Remind you what happens. We start at a saddle point. Then it becomes a spiral, or excuse me, a non-spiral sink. Right when the null lines merge, at that moment. And then when they're past merging, at some point it becomes a spiral sink, then it goes back to a saddle. Then it becomes a real source right now, and then a spiral source ultimately. Okay? Here's some code. Well, here's the bifurcation plane, the trace-determinant plane. Here's code that can have you do the eigensystem and matrix exponential for different values of mu, and show, for example, this picture. And I think that's probably good enough to end lecture B right there. Thanks for watching. I hope you enjoyed it.